So welcome back, and till now we have learned about different signals. So we have learned about continuous time signals and discrete time signals in the most general way, and we have seen the different classifications of elementary signals, both continuous and discrete time. And now we'll switch on to uh, the next area, that is called systems. So what is a system? As you are seeing now on the screen, a system is a box, or it is an entity which accepts an input, transforms that input into a required signal, that is called the output. So it transforms the input signal, it carries or does some process with the input signal, and gives out another signal which is called the output or the response. Okay, so here you can see that it accepts x of t and it transforms x of t into y of t. So y of t is a desirable output signal. Okay, so that's a system, and system often is actually described by an impulse response. You will learn about impulse response a little bit later. I just give an introduction or one line introduction to impulse response. Impulse response is actually represented by h of t. And so what is h of t? Suppose you have, instead of x of t, you have input signal as delta of t. So when you give such a signal delta of t, analog impulse to a system, the analog impulse signal get transformed, or system does some operations on that impulse, and you get an output which is called the impulse response. So when you give the input signal as impulse, you get the output of the system as an impulse response. So you can represent any system by its impulse response. That is why here h of t is marked. Okay, and later stage when we learn about Laplace transform, we'll transform this to that h of s, capital H of s, which is called the transfer function. Now we'll see what is the classification of systems. Okay, so first general classification, the most general classification is continuous time and discrete time systems. So what is continuous time system? That is, a continuous time system accept continuous time signals, and it gives out continuous time signals as output. So x of t is a continuous time signal which is being accepted by the system, and y of t is the continuous time system which is given out by the system. Both are continuous. Whereas if both are discrete, that is, it accepts discrete time signals and it gives out discrete time signals, such a system is called a discrete time system. You can see that x of t is being transformed to get y of t. Similarly, x of n is being transformed to get y of n. Now we have the lumped parameter and distributed parameter system. Okay, it is something not very important in the present context, but for some systems there are many components. Each component can be lumped or taken together at one point in space. So such systems are called lumped parameter systems, and if that is possible, they can be described by ordinary differential equations. Okay, and whereas for some systems it is not at all possible, for them parameters should be distributed, and for that the equations pertaining to them are partial differential equations. So why partial differential equations? Because parameters are not independent to each other. Each parameters depend on another parameter. So you have to describe such a system using partial differential equations. And the third classification is static and dynamic systems. So first we'll see what is a static system. A static system is said to be memoryless system. So if the response is due to the present input alone, that is, the output at any instant t or n depends only on the input applied at that instant t or the sample n. Okay, that is and that does not depend on the past or future values of input. That is what is happening now. You give an input, and at this instant the output will be at the same instant. You can see a few examples. That is, y of t is equal to x of t. So at time t is equal to 2 seconds, you have an input. At time t is equal to 2, you have the output y of t. Similarly, x square of t is equal to y of t. Y of t is equal to x square of t. So what is happening at 4 seconds? When you apply the input at time t is equal to 4 seconds, you get the output at the same instant for at t is equal to 4 seconds. Okay, similarly, x of n is y of n is equal to x of n. Okay, that is the input at n is equal to 1. When you apply input at n is equal to 1, you get the same output at the same instant itself, that is at n is equal to 1. Okay, so all these are examples of static systems. No memory, it does not depend on past or future values of input, only depends on the present value. That is, when you apply the input now itself you get the output. Okay, whereas memory systems are called, or dynamic systems are depends, the response depends upon the past or future inputs. So you can see the first example, that is y of t is equal to x of t minus 1. Suppose I take t as 4 seconds. So when I take t as 4 seconds, x of t minus 1, so 4 minus 1 is 3. That is, I'm applying the input at the time 3 seconds. So already I have taken t as 4 seconds, but the input is being applied. That is, input is a past input that has taken place at 3 seconds at t is equal to 3 seconds, but you get the output at t is equal to 4 seconds. So here you can see that the system depends upon the past input. Okay, that is, y at 4 depends on x at 3 seconds. Okay, now second example, that is y of t is equal to x of t plus x of t plus 2. X of t is okay, but you see the second term, that is x of t plus 2. Suppose I choose t as 1 second. Okay, so I expect the output at t is equal to 1 second, that is y of t, and it has two components. One of the input is one of the input it depends is at it is happening at the same instant itself, that is at t is equal to 1 second. But the second component, that is x of t plus 2, depends upon the time 3 seconds. That is 3 seconds is yet to happen. We are actually standing at a time t is equal to 1 second, and the second component, that output, that is y at 1 second, depends on a future input which is yet to happen, in the sense that will happen only at the after 2 seconds. That is, it happens only at when t is equal to 3 seconds. It happens only at that instant. Okay, so that depends on a future input. That is a dynamic system. Okay, and another thing is that you can see the third example, that is a dynamic system. You can see whenever you see a differential equation, that is a dynamic system, because differential equations, it pertains to the rate of change of input. Okay, you can see that here also it depends on the rate of change of input. So there is a variation in input, and whenever you see a differential equation, all differential equations are or represent dynamic systems. Okay, now y of n, similarly y of n, you can see that I'm taking the instant n is equal to 2 seconds. Okay, so I require the output at n is equal to 2 at the second sample, not 2 seconds, at n is equal to 2, that is at the second sample. So output at the second sample when n is equal to 2 depends on the input at the fourth sample, that is 2 into 2 is 4. Okay, that is again a future input. So that is again a dynamic system. Okay, and the fourth one is y of n is equal to x of n plus x of n minus. You can see that the first component, that is x of n, is actually the present input, but x of n minus 2 is a past input. Okay, so that also is a dynamic system. So a memoryless system is a static system, but a memory system is a dynamic system. Okay, the fourth classification, a very important classification, is the causal and the non-causal system. So already we have seen what is a causal signal and a non-causal signal. So what was a non-causal signal? A signal which does not have any values for t less than 0 was a causal signal. If a signal has a value for t or n less than 0, then that is a non-causal signal. Okay, so a perfect example of causal signal was u of t or u of n, which had signal only from t greater than or equal to 0 or n greater than or equal to 0. So whenever you want to ensure a signal to be causal or strictly causal, you have to multiply that signal with u of t. Okay, so which is a strictly anti-causal signal, that is u of minus t is strictly anti-causal. Okay, so so what is a causal and a non-causal system? See, a system is said to be causal or non-anticipative if the output of the system at any instant t or at any sample n depends only on the present and past values of input, but not on future inputs. That is, it is non-anticipative. That is, the output of the system depends on present and past values of input and not on the future values of input. So we'll see a few examples. That is, y of t is equal to x of t minus 2. X of t minus 2, you have learned from the previous discussion itself that it is actually a past input. T minus 2 is a past input, and x of t multiplied by 2 is a present input. So the y of t output depends on past as well as present inputs. Okay, whereas the second example, that is again y of t is equal to t into x of t, that also depends on the present input. There is no past as well as future, so that is again a causal system. And then you have y of n is equal to n into x of n, again that is a causal system. And the fourth example, that is y of n is equal to x of n minus 2 plus x of n minus 1 plus x of n. The first two components are past inputs and x of n is a present input. And one more thing is that all physically realizable systems are causal systems. Whatever you see, whatever circuits you see now in the lab as well as whatever devices you have, they all have circuits. All these are causal systems, because whatever systems you have or whatever physically realizable systems you have, they all depend on past as well as present inputs, and that is why they are all causal systems. Okay, so what is the importance of non-causal systems? If all systems that you have, you can touch, or what you see or what you use now are causal systems, then why do you want to learn about non-causal systems? Non-causal systems are anticipative systems, that is, they depend on future inputs also. That depends on future future inputs also. So perfect example is actually a weather forecasting system. Okay, weather forecasting, the word itself, that is anticipating you something, you're predicting something. So weather forecasting system is a perfect example of a non-causal system, because you are predicting something using some data. Okay, so such systems will depend on what future inputs. Okay, so such a system is a non-causal system. You can see the examples there, that is x of t is a present input, but x of t plus 2 is a future input. Okay, and the second example, the output, that is the output y of t depends on present as well as future input, that is t into x of t plus 1 is a future input. Likewise, the third one, that is y of n is equal to x of n plus x of 2n, that x of 2n is a future input, but whereas x of n is a present input. Okay, likewise, x square of n is actually a future input, but 2 into x of n plus 2 is a future input. So all these are non-causal systems. Okay, and one more thing you have to keep in mind is that is the easiest way, that is, for a causal system, its impulse response h of t is equal to 0 for t less than 0. In the case of discrete, h of n should be 0 for n less than 0. Okay, so that's a perfect way of describing a non-causal system. A non-causal is a causal system, that is, a causal system has its impulse response h of t equal to 0 for t less than 0, and for a discrete time system, causal system, h of n is equal to 0 for n less than 0. Okay, so causal systems are non-anticipative, whereas non-causal systems are anticipative. And the fifth classification is another very important classification, that is linear and non-linear systems. So a linear system obeys two principles. One is principle of homogeneity, and next is principle of superposition. Okay, so first we'll see what is principle of homogeneity. So the first check you have to conduct whether to ensure the system is linear or non-linear is the principle of homogeneity. That is very easy to perform. That is why we have to check that. Okay, so if principle of homogeneity is violated, then straight away you can declare that such a system is a non-linear system. Okay, so first check whenever you have a problem on hand, first check should be to check the principle of homogeneity. Okay, here again I will not be using boxes like the previous descriptions. Like these boxes I won't use, but I'll be using arrows, which actually I'll be using arrows which actually represent systems. Okay, if x of t leads to y of t, leads to means it gets transformed to y of t, so that arrow represents a system. So if x of t leads to y of t, suppose if I multiply or if I scale up the x of t input by a factor a, then output also should be scaled up or multiplied by the same factor a. That is the principle of homogeneity. So if I multiply the input by a, then output also should be multiplied by a. That is principle of homogeneity. Okay, so there is a corollary here. If a is equal to 0, if a is equal to 0, then what is the thing? That is, if I multiply any signal with 0, the signal is 0. So if we do not apply input, then the output also should be 0. So if input is 0 or if input is absent, then output should be 0. Okay, that is the best way of checking homogeneity. If you do not apply input and you do not get any response from the system, you can easily verify principle of homogeneity. That is, principle of homogeneity is verified. No input, no output. Without any input, if you have some output, then such a system is straight away a non-linear system. For example, a pre-charged capacitor. You do not have any connections across a capacitor, but since the capacitor is pre-charged, it has some charge inside, so across that capacitor you have some voltage. So such a pre-charged capacitor is an example of a non-linear system. Okay, now next is we have to check about superposition principle. Okay, that is, I have a signal x1 of t. If x1 of t leads to y1 of t, and if I multiply x1 of t by a, then the output also, that is y1 of t, also should be multiplied by a. That is, it obeys the principle of homogeneity. Next, I take another input x2 of t. You can apply any signal to a system. To the same system, I am applying another input x2 of t, and that should lead to y2 of t. If I scale up the input x2 of t by b, then the output y2 of t also should be scaled up by b. Okay, so that is again homogeneity. Now these two inputs, that is a x1 of t and b x2 of t, if I superimpose or if I add, I get a new signal x3 of t, and if that input is applied, that is two inputs are superimposed, I get a new input x3 of t. If that I apply to the same system, I should get a new output y3 of t. So if I apply a x1 of t plus b x2 of t, that is x3 of t, that should lead to a y1 of t plus b y2 of t, that is the new response y3 of t. That is superposition principle. So for a system to be linear, these two principles should be obeyed. Okay, so in the same way you can describe the same thing for a discrete time system. Just go through that. Here again you are verifying homogeneity as well as principle of superposition. Okay, now we'll see a few examples just to understand the theory we learned. That is, first one, that is d square y of t by dt square 2t y of t is equal to t square x of t. Okay, so with input x1 of t, so first thing is that I multiply throughout. So my input is x1 of t. If x1 of t is my input, then my output will be y1 of t. Okay, next I scale up the input by a factor a. Okay, that is, I multiply throughout the equation by a. So what is the result? A d square by dt square of y1 of t plus 2t a y1 of t equal to t square into a x1 of t. That is equation number 1. Similarly, you have, if you apply x2 of t, your response will be of y2 of t, and if I multiply the equation throughout by b, then I'll get equation number 2. Now I add 1 and 2, that is, I superimpose the two inputs. Okay, that is, I add 1 and 2 or superimpose those two. Okay, that is what is superimposition. That is, you apply inputs one at a time. First time you applied a x1 of t, Second time you applied b x2 of t. Okay, then you superimposed, that is then you added. Okay, then you mix the two signals, okay, which was independently applied earlier. Okay, so that you get a new signal. Okay, so when you add or superimpose those two signals, you can combine all the common terms. That is what you are getting here. That is a d square by dt square of y1 of t plus b d square dt by dt square y2 of t plus 2t a y1 of t plus 2t b y2 of t equal to t square a x1 of t plus t square b x2 of t. Okay, now I take out d square by dt square outside. You get is a y1 of t plus b y2 of t plus, then you take 2t, that is a y1 of t plus b y2 of t, which is equal to, I take 2t square outside, that is a x1 of t plus b x2 of t. And you can see that the two inputs you applied, and when you superimpose, you get a third signal, that is x3 of t. What is x3 of t? That is a x1 of t plus b x2 of t. And you apply such a superimposed signal to the system, you get a new output, that is y3 of t, and that is nothing but a y1 of t plus b y2 of t. Okay, now you can see that the same structure. Okay, that is initially your input was your output was y of t. Now d square by dt square of y of t became d square by dt square of y3 of t. What is y3 of t? That is a y1 of t plus b y2 of t plus, earlier you had 2t y of t, now you had 2t of y3 of t. What is y3 of t? That is a y1 of t plus b y2 of t equal to t square into x of t. Now what is the new signal? That is a x1 of t plus b x2 of t, that is x3 of t. Okay, that is, at last you can write it as d square by dt square y of 3 of t plus 2t y3 of t plus t square x3 of t. That is, the system obeys both homogeneity as well as superposition principle. That is, the system is linear. Okay, now same thing you can apply for the second equation, second problem. Okay, here again you apply the input a x1 of t, you get equation number 1. Okay, again you apply another input b x2 of t, you get the same equation number 2. You superimpose, that is you add equations 1 and 2, you get, okay, what you get, the thing, that is 2d by dt of a y1 of t plus b y2 of t plus, then 5 into a y1 of t plus b y2 of t equal to a x1 of x1 square of t plus b x2 square of t. Okay, you can see that for the LHS, the first term is the weighted sum of the outputs, second term also is the weighted sum of outputs, but you cannot say the same thing for the RHS, that is for the input. That is that is not a weighted sum of the inputs. Okay, if it was the weighted sum, it should have been a x1 of t plus b x2 of t the whole square. That was the new input you applied. Okay, that is a new signal x3 of t you applied. Okay, if you have applied such a new signal, that should have been x3 square of t. Okay, and that should have been a x1 of t plus b x2 of t the whole square, but that is not the resulting RHS. Hence the RHS side is not a weighted sum of the inputs, so the system is non-linear. Similarly, you can go through the third problem also. The third problem is also not a linear system. Okay, you can just refer that. Same thing, that is for a discrete time system, that is a non-linear system. And the sixth very important classification is time invariant and time varying systems. So what is time invariance? That is the system which makes, the property of a system which makes the behavior of the system independent of time. This means that behavior of the system does not depend on the time at which the input is being applied. A system is said to be time invariant or shift invariant. It has another name also, that is shift invariant, if its input or output characteristics do not change with time. Okay, that is, A time shift in the input results in a corresponding time shift in the output as shown in the figure. That is, if x of t leads to y of t, then if I delay the input by capital T seconds, then output also will be delayed by the same time t seconds. And you can see that the behavior of the system does not, or the behavior of the output does not change even if we delay the input by t seconds. That is very evident from the figure you see. That is, the first figure you can see x of t leads to y of t. If I delay the input by capital T seconds, then you can see the shape of the output remain the same, or the behavior of the system is remain the same. And only thing is that if input is delayed by capital T seconds, then output also is delayed by capital T seconds. We see a few examples. That is, y of t is equal to t square into x of t. That is, first we have to, this is a procedure to do the problem. First we have to delay the input by capital T seconds, only the input. What is input? That is x of t. That is, when I delay the input by capital T seconds, what I get is that I get a new, I describe that by y of t comma capital T, that is equal to t square into x of t minus t, because I delay the input by t seconds. Okay, that is, when I delay the input by t seconds, it is x of t minus t. Okay, that is equation number 1. Okay, then you have to delay the output by t seconds. Okay, that is, when I delay the output by t seconds, then y of t becomes y of t minus capital T. That is, the argument t is now replaced by t minus t. So y of t minus t is equal to, instead of t, the argument is now t minus t. So that becomes t minus t the whole square multiplied by x of t minus capital T. That is equation number 2. You can see that both are not the same. If input is delayed by t seconds, then output also should be delayed by t seconds. Okay, that is not the case. So 1 and 2 are not equal. So such a system is a time variant system. You can see the next one, second example. That is, first one, I delay the input by t seconds. I get y of t minus, y of t comma capital T is equal to x of minus 2t minus t. That is delayed by t seconds. Next, output is delayed by capital T seconds. That is, y of t minus t, that is, the argument t is now replaced by t minus capital T. That is, x of minus 2. What is t? T is now replaced by t minus capital T. That is equal to x of minus 2t plus, if you open the brackets, you can see that it is x of minus 2t plus 2 capital T. Again, you can see that both are not equal. That is, y of t comma t is not equal to y of t minus capital T. So that is a time variant system. You can see the third example. That is an example of a time invariant. In the same way you can delay the input, in the same way you can delay the output. You can see that equations 1 and 2 are the same. So such a system is a time invariant system. In the same way, example 4, that is, y of n is equal to x of n minus 2. First you delay the input by k samples. That is, x of n by 2 delayed by k samples is x of n by 2 minus k. That is equation number 1, which is given by y of n comma k. And then you delay the output by k samples. That is, y of n minus k, which is equal to, that is, argument n is now replaced by n minus k. That is, x of, instead of n, you have n minus k whole divided by 2. Okay, you can see that equation 1 and equation 2 are not the same. So that's a time variant system. Okay, you can see and easily understand what is the problem 5. Okay, now the next classification of a system is a stable or unstable systems. Okay, obviously you want to work with stable systems also. Even you don't want to work with a marginally stable system, because practically you want absolutely stable systems. So whenever you have to realize some systems, that should be absolutely stable system. Okay, stable system in the sense that should be Bibo stable. So what is Bibo stability? That is, for a bounded input, a system anyway accept a signal. A system, when it accepts a signal, it will give a response, or it will give an output. It will give an output. Okay, so if I apply a bounded input, then the output should be bounded. Okay, so what is the meaning of boundedness? Okay, what is the meaning of bounded? That is, the magnitude, when magnitude of the signal should be should be less than infinity, or that should be a positive real number when time t tends to infinity, or when time progresses, or when time elapses to, or time moves to infinity. Your magnitude of output also should remain or confined to some positive real number. So what is bounded input? That is, the magnitude of the input that you apply should be a value mx, which is less than infinity for all values of t. Similarly for discrete time signals x of n, the mode of x of n, the magnitude of x of n should be a number mx, which is less than infinity for all values of n. When you apply such an input to a system, if it is a stable system, it will give a bounded output. So what is a bounded output? Bounded output magnitude will be some other real positive number my, which is again less than infinity for all values of t. And or if it is a discrete time signal, the mode of the magnitude of y of n will be another number my, which is less than infinity for all values of n. Okay, now we will see a few examples. That is, y of t is equal to e raised to x of t, and x of t is specified, the range of x of t is given, that is mod of x of t is less than or equal to 8. That is mod of x of t in the sense x of t can accept negative as well as positive values. So what about e raised to x of t? E raised to x of t, when you apply that 8, it can accept negative as well as positive values. So e raised to x of t will become e raised to minus 8 to e raised to 8. So the output will be within will be from range e raised to minus 8 to e raised to 8. Okay, so you can see that your input is bounded. Input maximum magnitude is 8. The mode of the value is 8. Maximum value is 8. When you apply e raised to 8, your output is bounded. You get a number which is less than infinity. So just such a system is a stable system. So you apply a bounded input. That is most important. You should apply a bounded input to the system. And when you apply a bounded input to system, if the magnitude of output is bounded, or it's a value less than infinity, such a system is stable. Whereas you see the second, straight away you can tell that that's an unstable system. Why? Because y of t is multiplied by time with u of t. U of t is multiplied by t plus 5. So when time t tends to infinity, when time t tends to infinity, what happens? T plus 5 tends to infinity. When t plus 5 tends to infinity, y of t also tends to infinity. Okay, why? The whole magnitude of y of t depends on the magnitude of t plus 5, because u of t, you know the magnitude. What is the u of t magnitude? U of t is all ones from 0. For t greater than or equal to 0, u of t magnitude is 1. It's all 1 from t is equal to 0. It's a right-sided signal. Okay, so magnitude of u of t is 1. Okay, so whole y of t magnitude depends on t plus 5. Or if t plus 5 tends to infinity, then obviously y of t tends to infinity, and such a system is an unstable system. Okay, and another way of checking Bibo stability is that for a continuous time signal, the impulse response h of t should be absolutely integrable. Absolutely integrable in the sense, magnitude of h of t should be absolutely integrable. That is, when you integrate from t is equal to minus infinity to plus infinity, the value after integration, you should get a value which should be less than infinity. The integration should suffice to some value which is less than infinity. Similarly, for a discrete time system, the impulse response of such systems should be absolutely summable. That is, mod of h of n, when you perform the summation of mod of h of n, then that is n ranging from minus infinity to infinity, the value after the summation should be some value or some number which is less than infinity. Okay, now we'll see the example 3, that is h of t is equal to 2 plus e raised to minus t, the whole thing multiplied by u of t. Okay, so I told that whenever you multiply a signal with u of t, you are ensuring that the signal is a causal signal. Okay, that is that's the right-sided signal. So even if you perform the integration from minus infinity to plus infinity, as you are multiplying with u of t, your integration changes, or the limits changed from 0 to infinity, because u of t does not have any signal, or u of t does not have any value less than 0. So there is no meaning in performing integration from minus infinity to 0. Rather, it should be from 0 to infinity. So when you do that, when you perform the integration, I know you know how to perform that. Integration of 2 dt is 2t plus integration of e raised to minus 3t is e raised to minus 3t by minus 3, the whole within the limits of 0 to infinity. When you apply that, what happens when you apply the limits to the first component, that is 2t, that is the whole thing becomes infinity. So such a system is unstable. Okay, so you perform, if you have the impulse response with you see whether the integration suffices to some value which is less than infinity. If that is the integration is actually a value, if the answer of the integration is some value which is less than infinity, then such a system is stable. Okay, now we'll see the fourth example, which is of a discrete time signal, and that is y of n. Y of n is equal to a into x of n minus 7. Suppose if I replace the input x of n by the digital impulse, that is delta of n. You know what is delta of n? Delta of n have only a value that is only at n is equal to 0. Okay, so it has a value 1, that is at n is equal to 0, or when the argument is equal to 0, here the argument is n, that is n is equal to 0. So when you apply such a digital impulse to a system, you get a system response or the impulse response, which is represented by h of n. So h of n is equal to a into delta of n minus a. That is, the input is replaced by delta of n minus a. You get the output y of n, that is h of n. Y of n replaced by h of n, which is nothing but the impulse response. Okay, what is impulse response? When you apply the impulse as the input, you get the impulse response, that is h of n. Okay, now you have to see whether this signal is absolutely summable or not. You apply the definition, that is, you perform the summation from n is equal to minus infinity to plus infinity mod of h of n. Okay, you do that. You know that even if you apply, you do the summation from n is equal to minus infinity to plus infinity, you know that the delta of n minus 7 have only a value 1 at n is equal to 7. That is when the argument is equal to 0. That is n is equal to 7. So what is the value at n is equal to 7? Delta of n minus 1 is having a value 1 at n is equal to 7. What is the other value? That 1 is being multiplied by a. No other value exists at any other sample, at any other values of n. There is only one value, that is n at n is equal to 7. That is 1 multiplied by a is a. So when you perform 0 plus 0 plus 0 plus 0 plus, and only there is only value that is at n is equal to 7, all other values, it is all zeros. So when you add all infinite number of zeros plus a number a, what happens? The result is a. Now, is the system stable or not? You have a result a, but thing is that the value of a should be less than infinity. If the value of a is less than infinity, then the system is stable. If the value of a is infinity, then that is meaningless. That system is unstable. Okay. Now, similarly, the fifth example, you can see that 2 raised to n u of n. When you apply the summation, even if you perform from n is equal to minus infinity to plus infinity, you're multiplying. As you're multiplying by u of n, your summation suffices to 0 to infinity. Okay. And you can see that its summation from n is equal to 0 to infinity, 2 raised to n, that is of course equal to infinity. So such a system is unstable. And the last classification is invertible and non-invertible systems. Okay, so what is an invertible system? Suppose you have a system represented by t, which means that which stands for transformation. That is, x of t is being transformed to get y of t. Okay, now, or x of n is being transformed to get y of n. Okay, to that system you cascade another system which is having a transformation, that is t inverse. Okay, so when you cascade such a system, if you're getting the output which is same as the input you apply to the first system, then such a system is called an invertible system. That is, you cascade t with its inverse, and you get the output as the input to the first system. You get the output as the same input that you have applied to the first system, that is x of t or x of n. If that is happening, that the system is invertible system. Otherwise, the system is non-invertible. Okay, there is another way of examining whether the system is invertible or non-invertible. That is just you have to know what is one-to-one mapping and many-to-one mapping. So what is one-to-one mapping? That is a unique mapping. That is, each you apply different inputs to a system, if you apply x1 input, then you get y3, you get only y3. Okay, you apply x2, you get y4. You apply x3, you get y1. That is, you apply x4, you get y2. Okay, you never get y2 when you apply the input x3. You never get y3 when you apply the input x2. That is, each input corresponds to a unique output. Okay, or one input corresponds to only one output. Okay, that is called one-to-one mapping. So what is many-to-one mapping? That is, you can see that the input x2 as well as x3 corresponds to the same output y2. That is, two inputs corresponds to one single output, that is y2. That is, many input correspond to one output, that is many-to-one mapping. Okay, so a simple sense, a system following one-to-one mapping is an invertible system. A system following many-to-one mapping is a non-invertible system. I can tell examples of invertible systems as y of t is equal to 3x of t. Okay, that is, if you have value of x of t as 1, then y of t is equal to what? 1 multiplied by 3 is 3. Okay, so each input, 1 corresponds to 3, 2 corresponds to 6, 3 corresponds to 9, and 4 corresponds to 12. Similarly, the second question also, you have x of t. If you apply minus 3, you get minus 3 square is 9. 9 multiplied by 2 is 18. You get 18. Okay, but if you apply 3, x of t as 3, 3 square is 9. 9 multiplied by 2 is 18. That is, minus 3 and 3 corresponds to same output, 18. That is many-to-one mapping. Likewise, minus 2 and 2 corresponds to same output, 8. Again, many-to-one mapping. So such systems are non-invertible systems. Hope I have taken everything in these classification and systems. Okay, and I have described from the onset what is a system and different classifications. I'll give some more examples which you can solve at home. Okay, so thank you so much.